Hello and welcome to another of my videos about the derivative rules. In a previous video, I've already talked about sine and cosine, what their derivatives are and why. And the last video I made was about the quotient rule, and the last example I did in that video was to write tangent of x as sine of x over cosine of x, and then use the quotient rule on that to find the derivative. And it turned out that the derivative of the function tangent x is secant squared of x. And then I said I was going to leave the remaining three trigonometric function derivatives for you to try if you want, and wait until another video to tell you what they are. So this is that other video. This is the video where I will give you the derivative rules for the rest of the trigonometric functions, cotangent and secant and cosecant, and we'll try a few examples with those. And we will be using at least some of these basic, important, useful trigonometric identities. So it's important to know the relationships among the trigonometric functions, and which ones are reciprocals of the others, and how tangent and cotangent can be written in terms of sine and cosine, and then the so-called Pythagorean identities that relate the squares of some of the trigonometric functions. So let's derive, that is, let's figure out what the derivative of the secant function would be, because we can write secant of x as 1 over cosine of x. And we already have a rule for what the derivative of cosine of x is, and we have the quotient rule that we can use on something over something else, so we should be able to figure out what the derivative of 1 over cosine x is. So we are using the quotient rule here, which tells us to take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So here that would be cosine x times the derivative of 1, which is 0, minus 1 times the derivative of cosine x, which would be negative sine x, and that's all over cosine of x squared. Now we can clean that up a bit, because cosine x times 0 would just be 0, and then we have minus a negative or plus a positive 1 times sine x. So the numerator is really just the sine of x, and the denominator is the cosine of x squared, or cosine squared of x. And we could just leave it at that and say, okay, there it is, that's the derivative. But when trigonometric functions are involved, there's often more than one way of writing things. You can use those trigonometric identities to transform something into something else that looks different but is actually equivalent. So one way we can do that here is we can take this sine x over cosine squared x and split it up into sine over cosine times 1 over cosine. Because, of course, if you multiply that together, on top you get sine x times 1, and on the bottom you get cosine x times cosine x, or cosine squared x. So the sine over cosine would be the tangent of x, and then 1 over cosine would, of course, be the secant of x. So we do end up with tangent x times secant x. And this is the way the derivative of secant x is usually written. If you look up on a list of derivative rules, hey, what's the derivative of the function secant x? This is the way it's usually written, as the tangent of x times the secant of x, or it could be written in the other order, secant x times tangent x. Of course, with multiplication, it's commutative, so it doesn't matter which one comes first. So there's the derivative rule for the function secant x. The derivative of secant x is tangent x times secant x. And the remaining two rules, I'm just going to tell you what they are. They can be worked out similarly to how we worked out the derivatives of tangent and secant. It turns out that the derivative of cotangent x is negative cosecant squared of x, and the derivative of cosecant x is negative cotangent x times cosecant x. And if it helps you to remember these rules, notice that the three co-functions, cosine, cotangent, and cosecant, are the ones that have minus signs in front of their derivatives. Notice that the derivatives of tangent and secant involve secant and tangent, and that the derivatives of cotangent and cosecant involve cosecant and cotangent. Now, do you really have to memorize these derivative rules? That's something that when I've taught calculus, my students have naturally wanted to know. What are we going to have to remember? What do we have to know, like, for the test? So, in general, with mathematical rules or formulas or things like that, obviously, if they're not something that you're ever going to use ever again, then there's no real need to memorize them. But if they are something that you're going to have a use for again in the future sometime, whether on a test or in some later application or something, you kind of have three options. You can memorize the rules. You can commit the rule or the formula or whatever it is to memory. You can know how to figure out what the rule is, how to derive it for yourself. Or you can just remember that the rule exists, and if you need to know exactly what it is, you can look it up somewhere. You can look in your book, or you can Google it, or whatever. And all three of these have their advantages and disadvantages. Memorizing the rules, well, the nice thing about that is once you have it committed to memory, you can just immediately pull it out, and you don't have to take the time to re-derive it or go look it up. And the other nice thing about having the rules memorized is you know them forwards and backwards. Like, not only do you know that the derivative of tangent is secant squared, so anytime you need the derivative of tangent, you know that it's secant squared, but also whenever you see secant squared, you know, aha, that's the derivative of tangent. So if I were going the other way, like you will when you do integration, you know it that way. And that applies in other situations in math. Like learning the basic multiplication facts is important because not only do you have to remember that like 3 times 7 is 21, I mean, yeah, you can punch that into your calculator, but it also is handy to know that 21 is 3 times 7. So if you're in a situation where you are factoring and you see the number 21, you know that, hey, that number is what you get when you multiply 3 times 7. If you don't remember the rule itself, sometimes you can remember how to figure out what the rule is. Maybe you don't remember all those derivative rules, but you remember how we got them using the quotient rule on a way of writing the trigonometric function. And that way, instead of memorizing lots and lots and lots of individual rules and formulas and equations, you just remember some basic principles, and then you can put those principles together or use them to draw out the other things that you might need when you need them. And that way you kind of make those rules your own, and they're not just stuff that you memorized or tried to memorize. The third option, of course, is to know that the rules exist. You remember, oh, there is a rule for the derivative of this function, or there is a trigonometric identity for when you have this kind of a situation. And if you don't remember what that rule is, you can just look it up. And that might be the best way to go if you have a rule that you only use once in a while, like once every year or so. You need to know this trigonometric identity, so you just remember that there is such a thing, and you can go and look it up and see exactly how it goes. Anyway, let's go on and look at some more examples of these rules in action, putting these new trigonometric derivative rules together with some of the other derivative rules that we already know, like the product rule or the quotient rule, or in this case, we have a constant times a function minus another function. So the derivative of that whole thing, 4 secant x minus cotangent x, should be, well, it should be 4 times the derivative of secant x minus the derivative of cotangent x. And if you don't remember what those derivatives are, I've got them right here on the screen. We can look them up. The derivative of secant x is tangent x times secant x. And the derivative of cotangent x is negative cosecant squared of x. So altogether, f prime of x would be 4 tangent x secant x minus a negative, or plus a positive, cosecant squared x. So that's it. That's all there is to finding that derivative. Of course, if we didn't know or didn't remember the rules for the derivatives of secant x or cotangent x, we could have written secant x as 1 over cosine x, and written cotangent as cosine x over sine x, and used the quotient rules on those. Wouldn't have been nearly as easy, but we could have done it. Okay, how about this one? What's the derivative of the function sine x times cosecant x? Well, that looks like a job for the product rule. After all, we've got two things multiplied together there. That's a product. So the product rule would tell us to take the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. So we take the first thing, sine x, times the derivative of the second thing, and the derivative of cosecant x would be negative cotangent x times cosecant x, plus, now we've got the second thing its own self, cosecant x, times the derivative of the first thing. The derivative of sine x is cosine x. And right here where we got this minus cotangent x, we could write that as cosine x over sine x and bring the minus out in front. And then this sine x here over this sine x here, those cancel out. So we can simplify this a bit to minus cosine x times cosecant x plus cosine x times cosecant x. But you know what? Those are just the same thing, only one's negative and one's positive. They're opposites of one another, so they add up to 0. So the derivative does turn out to be 0. I mean, originally we got this big mess, but we were able to simplify that down, and here it really simplified down to 0. But wait, if we had been really on the ball, we might have noticed, before we did any of that differentiating and pulled out the product rule and all that, we might have noticed that sine of x and cosecant of x are reciprocals of one another. The cosecant of x is really just 1 over the sine of x. So if you multiply those together, you get 1. So our function f of x is really just the constant function 1 in disguise. And what do you get when you take the derivative of a constant function like 1? Well, you get 0. So sometimes, especially when trigonometric functions are involved, there can be more than one way of doing something. There might be a way of simplifying or rewriting a function in a form that's easier to differentiate. And if one person does that and another person doesn't, they might get different looking answers that really are equivalent, but it might take a little bit of cleverness to show that they're equivalent. So what about this example? F of x equals 2x over sine x. There is more than one way that we can go about finding the derivative of this function. One way would be to use the quotient rule. After all, the way it's written there, it sure looks like a quotient. So this looks like a job for the quotient rule, which would tell us to take the denominator times the derivative of the numerator, so sine of x times 2, minus the numerator times the derivative of the denominator, 2x times cosine x, all over the original denominator squared. So there's not much cleaning up or simplifying to do here. We can just write this as 2 sine x minus 2x cosine x all over sine squared x, and that's it. That's the derivative. And That is a perfectly good, perfectly legitimate way of doing it. Another way we could do this would be, instead of thinking of this function as 2x over the sine of x, we could think of it as 2x times the cosecant of x. After all, it's 2x times 1 over sine x, the reciprocal of sine x, but that would just be the cosecant of x. So if we write it that way, we don't have to use the quotient rule, but we should use the product rule. Now it's in the form of a product, two things multiplied together, 2x times cosecant x. So the product rule would tell us that the derivative of that whole thing is the first thing, 2x, times the derivative of the second factor, negative cotangent x cosecant x, plus the second factor, cosecant x, times the derivative of the first factor, 2. And might clean things up a little bit if we put the one that's negative second. So we can write it as something minus something else. So then it would be 2 cosecant x minus 2x cotangent x cosecant x. And we could say, okay, that's the answer. That is the derivative of that function. And there's nothing wrong with leaving it like that. But let's see if this and this, the two different looking answers that we got, are really the same thing. Is 2 cosecant x minus 2x cotangent x cosecant x really equivalent to what we got when we did it the first way? It should be. We should be able to show that. So we can take this cosecant x and write it as 1 over sine x. We can take cotangent x and write it as cosine x over sine x. And this cosecant x is also 1 over sine x. So this is a fraction with 2 on top over sine x on the bottom, minus this, if we multiply it all together to make one big fraction, has 2x cosine x on top and sine squared x on the bottom. And if we want to be able to combine these fractions to do the subtraction, they need to have a common denominator. And the way to get them to have the same denominator as each other is to take this first fraction and multiply it on top and on the bottom by another factor of sine x, so that it will have a sine squared x down here to match the denominator of the second fraction. So then it becomes 2 sine x over sine squared x minus 2x cosine x over sine squared x. And now that both fractions have the same denominator, we can combine them into 2 sine x minus 2x cosine x all over sine squared x. And that does match what we got when we did it the first way. So that's it for this video. The next thing is a very important and maybe a little hard to get used to rule called the chain rule. The chain rule is very important both for finding derivatives and because it kind of leads into other mathematical topics like implicit differentiation, related rates problems, and when you get to integration, things like U substitution and things like that all kind of relate to the chain rule. So I hope to, before too much longer, have a video where I explain how that works.